In this video, we're going to be looking at topic 11A, further kinetics, and this is the second half of the topic. So if you want to check out the content of the first half, please make sure to check the year 13 playlist on this channel and you'll find that video. So we're looking at the second part, and this is the IA2 chemistry course from Edexcel. So we're going to be looking at how to get a reaction mechanism by using what we know about the rate equation and a stoichiometric equation. We're going to be looking at SM1 and SN2 mechanisms and how we relate that to hydrolysis of halogenoalkanes, how we can determine the activation energy from experimental data, and also looking at heterogeneous catalysts. Now, this topic does also include two core practicals, which are core practical 9 and 10, but you can find a separate video on these on this YouTube channel. If you look at the year 13 playlist, you will see core practicals 9 and 10. So we've been looking at rate equations and orders of reaction in the previous video. So now we're going to take what we know and see how we can apply that to tell us something about a mechanism. Now, if we have a reaction taking place via one single step, so for example, reactant A and reactant B colliding to make a product, we call this an elementary reaction. Now, the thing is that majority of our reactions are not elementary reactions and they actually take place via a reaction mechanism. And we've discussed organic mechanisms in topic 4, topic 5, and topic 10. So you've seen the mechanism for nucleophilic substitution, for electrophilic addition, and other various mechanisms, and you're going to revisit that again in topic 15 and topics 18, 19 and 20 when you get into unit 5. Now, we cannot determine the reaction mechanism simply from the stoichiometric equation, and if we're not sure what we mean by that, we simply mean a balanced chemical equation. Okay, and in order for us to actually figure out the reaction mechanism, we must do this experimentally, and we can determine it using our orders of reaction with respect to each reactant. So let's look at an example. So if we have this stoichiometric equation, so NO2 plus CO gives us NO and CO2. We can figure out that our rate determining step is our rate equation, is the rate equals K NO2 squared. So from this, what we can figure out is that our rate determining step involves 2 molecules of NO2 and nothing else. So that's what these numbers are going to tell us, as well as the order. They tell us the number of molecules. So that's the whole point in getting the order of the reaction. So because the NO2 is the only thing that is in the rate determining step, that's the only thing that can be taking part, because we know if it is a zero order reactant, it has no effect on the rate, so it is not in our rate equation and therefore not in our rate determining step. And this order of second order tells us that we have 2 molecules. So we can figure out how many molecules and what molecules are in our rate determining step by using our rate equation. So if we take that information that we know, we could get 2 possible rate determining steps. So we can have 2 molecules of NO2 reacting in 2 different ways. We could either make N2O4, or we can make 2 molecules of NO and 1 oxygen molecule. Okay, now there's no exact way for us to know which one of these is correct just from the information that we've been given. If we were trying to work out a mechanism, we would do lots of other reactions and lots of other data collection, but we're just going to take this very generally and we're going to look at this second example because this is a little bit easier for us to see. So what we want to look at is our possible mechanism could be that we have our 2 molecules of NO2 reacting to form our 2 molecules of NO plus oxygen. We know that our other reactant is carbon monoxide, so we could have carbon monoxide reacting with oxygen to make carbon dioxide, and then one of our molecules of our NO reacting with oxygen to form NO2. And because this is our slow step, remember this is our rate determining step and the other 2 are fast. Now, the reason why I've selected these steps is because our proposed mechanism has to balance out to make our stoichiometric equation. So this equation at the top here is our target. And we can put forward any mechanism and any number of steps that we feel is appropriate as long as they all balance out to make that molecule. To make that equation. So for example, one of my NOs is going to balance out with the NO in step 3. So we have steps 1, 2, and 3, and then the target. Our oxygen from step 1 is going to balance out with the oxygen on step 2. And one of our NO molecules is going to balance out with and step 1 is going to balance out with step 3. And then those cancellations are going to give me, and then my oxygen atoms, they're going to give me my target equation. Now, in reality, the mechanism for this reaction is completely different. This is not the mechanism. However, that is not the point in these questions. The point in these questions is to provide a proposed mechanism. So it's what do you think could happen? It is not asking you to be a person that can determine every single mechanism just simply by looking at the rate determining step. We can't do that. What we can do, however, is use our knowledge of chemistry and use our reactions and what reactant could be formed and what products could be formed in order to determine a possible mechanism. Now, these particular questions, they can come up and they're usually maybe 3 to 4 marks, but one common question is determine a possible rate determining step. Because although we can determine our 2 reactants, or 2 or 3 possible reactants, we don't necessarily know what the products are going to be made in a mechanism, because typically they are not the products in our stoichiometric equation. So as long as your mechanism cancels out to give you the stoichiometric equation, then it is a perfectly valid answer and you would get given the marks. As long as you do not include incorrect chemistry, you can still get the marks. Now, moving on, we're going to look at SN1 and SN2 mechanisms. Now, if you remember back to topic 10, where you were looking at the hydrolysis of halogenal-alkanes, and you were able to give information about why the iodo alkene was the fastest, because it was to do with the Ci bond being weak, and then the CBr bond and then the CCl bond, and you could explain that using bond energies. And at the time, what we said was that tertiary were the fastest, followed by secondary, followed by primary. And we said at the time, you do not need to be able to explain why. This is going to go into a little bit of detail as to why, and it is to do with the type of mechanism that they undergo. So if we have the alkaline hydrolysis of 2-chloromethylpropane, this being a tertiary halogenoalkane, we can then use this equation and we have this rate equation happening here. Now, the reaction is first order with respect to the tertiary halogenoalkane, and we would find that out from our rate data, and it is 0 order with respect to the hydroxide. So that is why the hydroxide does not appear in the rate equation. This means that the rate determining step only contains the halogenoalkane. Okay, and what actually happens is we get the halogenoalkane being ionized, and this is a slow reaction. Remember, your rate determining step is your slowest step. So the slow ionization of the halogenoalkane happens where we make these 2 molecules here, and one being positively charged and one being negatively charged, and then we get a fast attack by the hydroxide ion into our carbocation here to form our alcohol. And that is the product that we want to make. And what happens, or what we call this, is an SN1 reaction. And SN1 stands for substitution, nucleophilic, unimolecular, meaning this is a nucleophilic substitution reaction and we only have one molecule present in the rate determining step. So this unimolecular is referring to the molecules in the rate determining step, and it occurs via a carbocation intermediate. So this molecule here is our carbocation intermediate. So we have two clear steps happening here because I only have one molecule in my rate determining step. If we compare this to the hydrolysis of 1-chlorobutane, with this being a primary halogenoalkane, we get the following chemical equation, making our alcohol, and we get this rate equation here. Notice that there are two molecules here. So this tells us that we are first order with respect to the primary halogenoalkane and also first order with respect to the hydroxide. This tells us that the rate determining step contains both the halogenoalkane and the nucleophile. So remember, a nucleophile is a substance that is attracted to an area of low electron density, so it's going to be negatively charged, in this case our OH ion. And the mechanism for this, you can see that we have a difference here, that we have a mechanism going through a transition state as opposed to the carbocation intermediate. And what that basically means is that the bond between the carbon-chlorine is being broken at the same time as the bond between the carbon and oxygen is forming. So for a small period of time, this carbon has 5 bonds, and so your transition state is negatively charged. And eventually what happens is the hydroxide group enters and the chloride group leaves, and we end up with our alcohol and our chloride ion being our other product. Okay? And we call this an SN2 reaction. So this is substitution, nucleophilic, bimolecular this time, meaning we have 2 molecules in the rate determining step, as opposed to the unimolecular that only had 1. And this is a continuous one-step reaction. So that is very different to the SN1 mechanism. SN1 mechanisms are 2 steps with a carbocation intermediate, and SN2 is 1 step with the transition state. So just be aware that the 1 and the 2 in SN1 and SN2 refer to the number of molecules in the rate determining step, not the actual steps of the mechanism. Now we can talk about activation energy, and we know that activation energy of a reaction represents the energy that the colliding particles must have in order to reach the energy level, in order to get a successful collision. And now we can change that slightly, and we can say it's the energy that they need to obtain, they must obtain in order to reach the energy level of the transition state. So the transition state is this peak at the top here. So we've drawn these reaction profiles since IGCSE, and what we know is that the distance between the reactants and the top of the peak is our activation energy. And once we get to the top of that, we make our transition state, and then the reactants can form the products. And as they do this, they're going to release energy. Now, we've previously discussed catalysts back in topic 9, and you've also discussed them in IGCSE. And we know that a catalyst is a substance that provides an alternative pathway that has a lower activation energy than the original route. Please, please, please remember to always say alternative pathway. Do not simply say it lowers the activation energy, because you will lose marks. So when they provide this alternative pathway with the lower activation energy, this is going to allow more molecules to have the energy that is above the activation energy, so you get more collisions happening because of this lower energy route. And catalysts can be divided into two groups. We can have homogeneous catalysts, or homogeneous catalysts, however you wish to pronounce it, and then we have heterogeneous catalysts. And you've probably come across both of these groups before, you potentially just did not know them. We're also going to revisit this back in topic 17. Now, a homogeneous catalyst is when they are in the same phase as the reactant. So this homo means same phase. And some examples would be the iodination of propanone. So that's catalyzed by hydrogen ions. Okay, and we'll discuss that in more detail later on in this course. So we're being catalyzed by an acid. You have destruction of ozone being catalyzed by chlorine-free radicals, which are all in gaseous forms. And if we have peroxide disulfate and iodide ions being catalyzed by iron 2+. And we'll discuss these more when we get into topic 15 and topic 16, we're talking about redox reactions. The key one that we want to cover here is heterogeneous catalysts, and these are in a different phase. So this hetero means different. And the two major examples that you have to know, that again we will discuss later in topic 17, particularly the contact process, are the Haber process, which makes ammonia, and it uses an iron catalyst, and the contact process makes sulfuric acid, and it uses a vanadium oxide catalyst. But we'll discuss that later on in topic 17. We're going to put our focus onto the Haber process. So we have one nitrogen molecule reacting with 3 hydrogen molecules to make 2 molecules of ammonia, and this is an equilibrium reaction. We discussed that back in topic 9 when we have the conditions, but what we want to look at now is what the catalyst does in terms of how it actually works. So the iron forms something known as an interstitial hydride with the hydrogen molecules, and basically what that means is the iron bonds with the hydrogen and holds the hydrogen in place, and by holding it in place it allows the nitrogen to collide with the hydrogen ions and then react. Okay, and the 3 main stages in catalysis, which in other words means the catalyst working, are known as adsorption, reaction, and desorption. So if we go through what these 3 things mean, adsorption means the reactants being adsorbed onto the molecule, onto the surface of the catalyst. Please be aware that it is adsorbed, not absorbed. If you write absorbed, you will lose the mark. It's adsorbed. And that means that they are being held onto the catalyst. The reaction, the second part, is the actual physical collision taking place. So this is the reactant molecules being held in a position by the catalyst, because remember we're thinking about not only energy but also orientation, and it is held in that position in order for them to react. Once they've reacted and formed the products, we get desorption, where the products leave the surface. So let's look at what that actually looks like. So one of the reactants, in this case our green reactant, is going to be adsorbed onto the surface of the catalyst here, and that's step 1. Step 2 is the yellow molecule approaching the green molecule, and then we get the reaction taking place in step 3. So you can see that we're forming our products here, and that is forming bonds here and breaking bonds here. And then once the products are formed, they are desorbed from the surface, and they are then released back into the mixture. So a catalyst, or a heterogeneous catalyst, works by holding one of the reactant particles in place by adsorption to allow the other reactant particle to actually react with it. Another type of catalysis that we need to look at is something called autocatalysis. And that, as you could probably figure out, means it is something that is automatically catalyzed by, in this case, one of its products. So a common example that we see is the oxidation of ethane dioic acid by acidified potassium manganate 7. Now, don't worry too much about this reaction in terms of being able to memorize it. You're not expected to memorize it. What you are expected to be able to identify is the catalyst and how it works. So this particular reaction is quite slow at room temperature. However, it is catalyzed by the manganese ion, and you will see that the manganese ion is one of the products. So the reaction is very slow at the start, and it will still happen at room temperature, but slowly. As we then form more product, we are forming more of the manganese, and the manganese then starts to act as a catalyst, and it will be made in an amount that is enough for it to react as a catalyst, and it will speed up the reaction until all of the reactants are used up and the reaction stops. So autocatalysis being the reaction being catalyzed by something it is making. And we can show this on a graph. So your concentration of your reactant, you can see the reaction starts off slowly at room temperature. The reaction is then going to speed up because I have made enough of the manganese in this case, and then eventually the reaction is going to slow down and stop because the reactants have been used up. Now, this is the same graph for any autocatalyzed reaction. I'm just discussing it in terms of the reaction that we've just looked at. So it starts off slowly at room temperature. It starts to speed up because I've made enough of my manganese that it acts as a catalyst. And the reaction will go quickly, so you can see the line get steeper, which means a faster reaction. And then eventually the line starts to level off, and we get this reaction slowing down before eventually stopping because all of my reactants have been used up. Now let's look at the effect of temperature on a rate constant. So there are two key reasons why increasing the temperature is going to give an increased rate of reaction. Now you discussed these back in topic 9, and the first one is that we get an increase in the fraction of molecules with an energy greater or equal to the activation energy. So this is very important that we're looking at the energy, and we discussed this using a Maxwell-Boltzmann distribution. So you had something that looked like this for T1, and for T2 the peak was lower and shifted to the right. And what we see is if this is our activation energy, this section alone would be the fraction at T1, whereas both sections would be the fraction of molecules with the energy greater than the activation energy at T2. So we're increasing that fraction, making sure that more molecules have an energy that's greater than the activation energy. The second reason why increasing temperature causes an increased rate is to do with the frequency of collisions increasing. And this is because the molecules or the particles have more energy. So the more energy that the particles have, the more likely they are going to move around and the more likely they are going to hit each other. But remember, to get a successful collision, the collision has to be above the activation energy and it has to be in the correct orientation. So actually the frequency of collisions has almost an insignificant effect on the rate, because you can get a large amount of collisions but not actually get any products being formed. So we're only going to be looking at the increase in fraction of molecules with the energy greater than the activation energy, and that's why you looked at that in topic 9. Now we can use an equation called the Arrhenius equation to express the relationship between temperature and the rate constant. And this equation here is the Arrhenius equation. Now you'll be very glad to know this will either be in your data book or given to you in the question. You are not expected to memorise this. If we just go through what each of the terms are, so K we know is the rate constant. We've been discussing that a lot in this topic. A is something called the pre-exponential factor, and this just measures how many collisions occur regardless of their energy. We're not too worried about that number just now. We have EA, which is the activation energy. We have R, which is the gas constant, and we met that back in PV equals nRT. And we have T for temperature, and making sure that temperature is always in Kelvin. Now, when we're actually wanting to use the Arrhenius equation, it is not much use to us in this current format. So what we want to do is we want to take the natural logarithm of both sides of the equation. And what we can then do is we get an expression that can be linked to the equation of a straight line. So we get this expression here, and we can link each of these. So that is y, this is m, that's x, and this is c. And we can then, because we can link it to the equation of a straight line, we can plot a graph, and then we can determine key information using that graph. So what we do is we plot ln k against 1 over t, and we get a nice straight line. And the gradient of this straight line is going to be equal to minus EA over R. So we can experimentally determine the activation energy for a specific reaction. Now, what we do with this reaction is we find out the rate constant at lots of different temperatures. And what we can then see is what the activation energy would be for a particular reaction. So we're linking activation energy, temperature, and rate constant all together. So if we have a table that looks like this, and this is for the reaction of the peroxydisulfate and iodide ions. So we have this equation here. And what we've done is we've carried out a number of different reactions at different temperatures, and we have determined the rate constant at each temperature. We then take the natural log of the rate constant, and you can see we go from all these decimals to nice easy numbers to work with. Notice that they are all negative. Then we take 1 over T, which is in Kelvin, and we get our numbers here where we have our decimals, and this is going to be our X and our Y axis. We can then plot these on a graph, and your graph will always look like this. It will always be a negative line, which would be if you were to draw the 4 quadrants of graph paper, you would have it in the lower right quadrant. So you have negative numbers for your y-axis going down, and then your 1 over t at the top. And you can see that we get this lovely straight line, and we can then determine the gradient of the line. To determine what points to use, the best thing to do is to look back at the table, and as long as the point lies on the line, you can then use the values from the table. So in this reaction, we've used the first and the last values because both of them lie perfectly on the line. Now the y-intercept, so where we cross the y-axis, that is equal to the natural log of A, remember A being our pre-exponential factor, but we're not particularly interested in that at this point. It's good to know that that's what it is, but we're more interested in the gradient. So I can determine what the gradient is using y2 minus y1 over x2 minus x1, and I get the value of minus 4,538. And then I simply rearrange my equation of minus EA over R to determine what the activation energy is, and I get an activation energy of positive 37.7 kilojoules per mole. So for this particular reaction, the activation energy is this value. So this is the way that we can graphically and experimentally determine the activation energy for a reaction. So let's finish up by looking at some past paper questions. What you will find is that there will be lots of questions on rate equations, rate determining steps, orders, and determining orders, you probably will find that there's not a lot of questions on the activation energy and the Arrhenius equation because they are new to the specification, but you can check the domestic papers. So this is linking into the reaction that we were actually looking at in the first video. So we have our nitrogen 2 oxide reacting with hydrogen to produce our nitrogen and water. And these were questions from the previous video. So this is our equation and our rate equation. So part C in this question is asking why, or there's one more step in the reaction mechanism. So there's more than one step. Suggest why this reaction is unlikely to take place in a single step. So remember, we're looking at the rate determining step here, and our numbers tell us that there are 3 molecules in the RDS. And we can see from our stoichiometric reaction that we're getting 2 moles of NO and 2 moles of H2. Don't let that throw you. Remember to be linking this to the rate equation. So because we have 3 molecules in our RDS, the chances of all 3 of those molecules colliding in the correct orientation with the correct energy is very unlikely. So that's basically all we're looking to say here. So the possibility of 3 molecules colliding with the correct orientation and energy is low, or it's unlikely that they will react or something to that effect. So the first step in the 3-step reaction mechanism is shown below. So we have 2 molecules of the NO reacting to form N2O2. And the second step is the rate determining step. So suggest an equation for the rate determining step and justify it. So in this case, we're looking at our rate equation. So we have KNO2H2. So we know that we're going to have our information being all of our molecules, taking part in the reaction. So basically we've used our 2 molecules of NO. So we have this N2O2 gas reacting with the hydrogen to give us various different products. We're going to say that we're going to make nitrogen and H2O2. There's various different answers that you could give for the products that are formed, just as long as they balance out here. Okay, and the reasons why is the rate equation must include all the species up to and including the rate determining step. So in this case, we've already reacted the 2 molecules of the NO to make the N2O2. For the third step to be the second step to be the rate determining step, it has to react with what's left over. We only have 2 molecules of NO in our stoichiometric equation, so we can't add any more here. We're wanting to react it with the hydrogen to make our 2 products here. And then, of course, there would be a third step to give us what we want to actually react. So there you can see the mark scheme. And then we're going to finish off looking at the June 2018 paper. So this reaction is about the reaction kinetics of the iodine clock reaction, and that is one of the core practicals, core practical 9. And it involves iodate and iodide ions in acidic solution, and it uses this particular equation. So we've been able to then have a graph of ln K against 1 over T. So of course, we're looking at our Arrhenius equation here. So the Arrhenius equation can be expressed as this. Remember I said that you would get this in your questions. So there you've got Y, M, X, and C. So from the gradient in the graph, determine the activation energy for this reaction. So the first thing that we need to determine is what the gradient is. Now they are quite lenient here in making sure that you get the correct points. So you're probably going to want to use this point and that point because they are perfectly on the line. And you can work out the gradient to be y2 minus y1 over x2 minus x1, and using any of the points you get a value of 19,500. So when you rearrange, you're going to get your value being your gradient times the gas constant, and that would give you a value of 162,000. The two negatives will cancel each other out, and of course this is in joules per mole. We want to convert that to kilojoules, so our activation energy, we divide by 1,000 and cancel out the negative signs, is going to be 162 kilojoules per mole, and that would be for 3 marks. And then part 2, give a reason for the point at lnk equal -7 not being included on the line. So if we just go back here, you can see this point. Why is it not on the line? Well, you can clearly see that it looks anomalous in comparison to all the rest of the points. All of the other points lie either directly or just ever so slightly off the line. So that is an anomalous point. And of course, we don't include an anomalous point in a line of best fit. And there you can see the mark scheme for those questions. So that's everything for topic 11A. Hopefully everything has made sense, and please feel free to have a look at the textbook and do some practice questions. If you have any questions, please also feel free to leave a comment below, and we look forward to seeing you back on the channel soon.